The universe is a place of endless mystery, a cosmic stage where the laws of physics sometimes seem to bend in ways we can't yet explain. Out there, beyond the familiar glow of stars and planets, lie phenomena so strange, they challenge everything we think we know about reality. Picture this black hole so massive they warp the fabric of space-time, radio signals from deep space repeating in patterns we can't decipher, galaxies that spin in ways that defy gravity itself. These aren't just plot points from science fiction, they're real, they're happening right now, and they're waiting for us to unravel their secrets. What if I told you there are at least 25 cosmic anomalies, each one more baffling than the last, that even the brightest minds in science can't fully explain? These aren't just oddities, they're cosmic puzzles that rewrite the rules of the universe as we know them. Some of them whisper clues about the origins of existence, while others hint at forces and dimensions we've yet to discover. And the most thrilling part, you don't need a telescope or a degree in astrophysics to join this journey. All you need is curiosity, a sense of wonder, and the willingness to question what's possible. That's exactly what we're about to do together, dive into the deepest, most mind-bending corners of the cosmos, where the ordinary becomes extraordinary and the impossible seems just within reach. From rogue planets hurtling through the void to eerie voids in space where nothing, not even light, escapes, these anomalies don't just defy explanation, they invite us to rethink our place in the universe. So buckle up, because by the end of this journey, you'll see the night sky not just as a scattering of stars, but as a living, breathing mystery box filled with questions that are begging to be answered. Are you ready to explore the unknown? Let's begin. Imagine tuning an old radio late one night, scanning through static, when suddenly a burst of sound so loud and clear it makes you jump. That's essentially what happened to astronomer Jerry Amon on August 15, 1977, when Ohio State University's Big Ear radio telescope picked up something extraordinary. A 72-second radio signal so powerful, so unlike anything else in the cosmos, that Amon circled it on the printout and scribbled one word in the margin: wow. This signal, now known as the WOW signal, came from the direction of the Sagittarius constellation, roughly 120 light-years away. What made it special? For starters, it hit a frequency of 1,420 MHz, a range scientists had long considered a likely candidate for interstellar communication, since hydrogen, the most common element in the universe, emits energy at that exact frequency. The signal was also narrowband, meaning it was focused on a single frequency, unlike the broad, messy static of natural cosmic noise, and then, just like that, it vanished. Despite 45 years of searching, we've never heard anything like it again. So what could it have been? Some argue it was a natural event, like a comet's hydrogen cloud reflecting sunlight, though no known comets were in the area at the time. Others point to human-made interference, but the signal's intensity and frequency don't match any satellites or aircraft. Then, of course, there's the electrifying possibility: was it deliberate? An intentional broadcast from another civilization? The signal's brevity and uniqueness leave the door wide open. Even today, the WOW signal stands as a tantalizing enigma, a cosmic whisper that refuses to be forgotten. One that reminds us just how much we still have to discover in the vast, silent ocean of space. Now picture an invisible river, vast beyond comprehension, pulling entire galaxies off course like leaves caught in a cosmic current. Astronomers call this dark flow, and it's one of the most perplexing discoveries in modern cosmology. Here's what makes it so strange. Galaxy clusters, some weighing as much as 1,000 Milky Ways, are all being dragged in the same direction at breakneck speeds, as if something massive beyond the edge of our observable universe is yanking them toward it. The first hints of this phenomenon emerged in 2008 when scientists studying the cosmic microwave background, the faint afterglow of the Big Bang, noticed something odd. The microwaves showed tiny temperature shifts, suggesting galaxy clusters were moving in unison at nearly 2 million miles per hour. That's far faster than the expansion of space alone could explain. Even stranger, the pull seems to originate from a region of nothingness, a void where no known supercluster or concentration of matter exists. This mystery ties into an older cosmic puzzle, the Great Attractor. Decades ago, astronomers noticed our local galaxies, including the Milky Way, were being pulled toward a gravitational anomaly in the constellation Centaurus. But here's the twist: a dark flow's source lies even farther out, suggesting the Great Attractor might just be a small part of something much larger. Some theories propose unimaginable structures beyond our cosmic horizon, perhaps a supermassive cluster of galaxies trillions of light-years away, or even the gravitational tug of another universe in a multiverse. Skeptics argue it could be a statistical fluke, but the data holds up. If dark flow is real, it shatters a fundamental assumption that the universe is roughly the same everywhere. Instead, it hints at a cosmos lopsided with unseen mass, a place where the familiar laws of physics might not apply beyond what we can see. It's a humbling reminder: we've mapped just a fraction of existence, and the universe still has secrets we're only beginning to sense. Starlight usually follows predictable rhythms, steady pulses of brightness that tell astronomers about a star's size, age, and composition. But then there's Tabby's star, officially known as KIC 8462852, a cosmic rebel that refuses to play by the rules. Located roughly 1,400 light-years away in the constellation Cygnus, this unassuming star dims in wild, irregular patterns, sometimes dropping in brightness by up to 22%, far more than any known natural phenomenon could explain. When astronomer Tabetha Boyajian first spotted these bizarre fluctuations in 2015, the data was so strange, her team nicknamed it the most mysterious star in the galaxy. The anomalies started with NASA's Kepler Space Telescope, which monitors starlight for the telltale dips caused by orbiting planets. Typically, a planet blocks less than 1% of a star's light. But Tabby's star showed dramatic, jagged drops lasting days or weeks with no predictable rhythm. Even stranger, long-term studies revealed the star's overall brightness has been fading for over a century, defying all conventional stellar models. Scientists scrambled for explanations: maybe a swarm of comets, a debris field from a catastrophic planetary collision. Then came the electrifying hypothesis: could it be alien technology? Some researchers suggested the dimming might match theoretical Dyson spheres, massive energy-harvesting structures built by advanced civilizations. The idea wasn't entirely fringe. Even famed astrophysicist Freeman Dyson once theorized that a sufficiently advanced society might construct such megastructures to capture a star's power. But when follow-up observations failed to detect the infrared heat such structures would emit, the excitement dimmed, though the mystery only deepened. Recent studies offer new twists. Dust, it turns out, might be the culprit, but not ordinary dust. Tabby's star's light patterns suggest microscopic particles unevenly distributed in clumps, unlike the smooth rings around young stars. Some propose a shattered moon or a captured rogue planet slowly disintegrating, while others point to magnetic field anomalies unique to the star itself. Yet every explanation has gaps, leaving astronomers circling back to one unsettling truth: we've never seen anything quite like this. What makes Tabby's star so captivating isn't just its odd behavior. It's the humbling reminder that even in an era of high-tech telescopes, the cosmos can still surprise us. Whether it's an undiscovered natural phenomenon or something far more speculative, this star challenges us to keep questioning, keep searching, and stay open to the possibility that the universe might be stranger than we've ever dared to imagine. The universe is unimaginably vast, with billions of galaxies, each containing billions of stars, many of which likely host planets in the so-called Goldilocks zone, where conditions are just right for life. Given those odds, the cosmos should be teeming with civilizations, their signals crisscrossing the void, their artifacts littering nearby star systems. And yet silence, no radio broadcasts, no alien megastructures, no visitors knocking on our cosmic door. This eerie contradiction is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" At its core, the paradox forces us to confront two unsettling possibilities. Either we're missing something fundamental about how life arises, or we're tragically alone. The first theory, known as the Great Filter, suggests there's some catastrophic barrier either behind us or ahead that prevents life from flourishing. Maybe simple life forms easily, but intelligence is vanishingly rare. Or perhaps civilizations inevitably destroy themselves before reaching the stars. If the filter lies in our past, it means we've beaten cosmic odds. If it's in our future, well, that's a sobering thought. Then there's the zoo hypothesis, the idea that advanced civilizations know we're here but deliberately avoid contact, treating Earth like a nature preserve. It's a cosmic version of look but don't touch, with humanity as the unaware exhibit. Other theories are even wilder. Maybe aliens exist as stealthy AI, exploring in ways we can't detect, or they've moved beyond physical reality into digital realms we can't perceive. Some argue we're simply too early, that the universe is still young, and the great age of cosmic civilizations lies far in the future. Yet the silence might have a darker explanation. What if expansionist civilizations inevitably wipe others out? This dark forest hypothesis, inspired by survival instincts, suggests every species stays quiet to avoid attracting predators. In this view, broadcasting our location, as we've done with radio and TV signals, might be naively reckless. The Fermi Paradox isn't just about aliens, it's a mirror. Every possible answer forces us to question humanity's place in the cosmos. Are we special, lucky, doomed? Until we find evidence one way or another, the paradox remains one of the most profound puzzles in science, a humbling reminder that even in an infinite universe, some questions still echo unanswered. Deep in the cosmos, there are explosions of energy so intense they outshine entire galaxies, and they last barely a millisecond. Fast radio bursts, or FRB, are among the most fleeting yet powerful phenomena in the universe, packing more energy than the sun emits in 80 years into a burst shorter than the blink of an eye. First discovered in 2007, these mysterious signals race across billions of light years, vanishing before scientists can pinpoint their exact origins. But here's what makes them truly bizarre. Some repeat. Take FRB 1211, for instance. Located in a dwarf galaxy 3 billion light-years away, this burst wasn't a one-time event. It flickered on and off like a cosmic strobe light, flashing dozens of times in irregular patterns. Other repeating FRBs, like the famous 1812 in a distant spiral galaxy, pulse with such precision they almost seem engineered. The leading natural explanation: magnetars, ultra-dense, highly magnetized neutron stars that occasionally unleash catastrophic starquakes, sending shockwaves through space-time. In 2020, astronomers even caught an FRB erupting from a magnetar in our own galaxy, offering tantalizing evidence, but not all bursts fit this mold. Some are far too energetic, or their repeating patterns too complex, leaving room for wilder theories. Could some FRBs be artificial? The idea isn't as far-fetched as it sounds. A sufficiently advanced civilization might use focused beams of energy, perhaps for propulsion, communication, or even as a cosmic lighthouse. The burst's brevity and frequency could be the signature of technology operating on scales we can't yet comprehend. But before we jump to extraterrestrial conclusions, there's another twist. Some FRBs arrive with a strange shroud of turbulence, as if passing through dense plasma clouds near black holes or the wreckage of ancient supernova. The truth is, FRBs are more than just cosmic oddities, they're probes. Each burst carries encoded clues about the invisible cosmic web, the vast filaments of gas and dark matter stretching between galaxies. By studying how these signals distort as they travel, scientists are mapping realms of the universe we've never seen. Yet for every answer, a new question emerges. Why do some repeat while others vanish forever? What could generate such staggering energy without self-destructing? The more we learn, the clearer it becomes. These millisecond flashes aren't just anomalies, they're messages from the universe's most extreme environments, written in a code we're only beginning to crack. High above Earth, hidden in the perpetual darkness of space, something may be watching us, or at least that's what conspiracy theorists have claimed for decades. Meet the Black Knight satellite, a shadowy object allegedly orbiting our planet for thousands of years, whispered to be everything from an ancient alien probe to a relic of a lost human civilization. The legend began in the 1950s when newspapers reported odd radio signals supposedly intercepted by researcher Nikola Tesla, followed by claims that the US Air Force had detected a mysterious, dark satellite in polar orbit, an impossible feat for 1954 technology. But here's where the story twists. In 1960, Time magazine published images of a strange, tumbling object caught on camera by the U.S. Navy, debris from a Discoverer satellite, though enthusiasts insisted it was the Black Knight. Decades later, astronaut Jerry Ross, during a 1998 Space Shuttle mission, filmed an unidentified object drifting near Earth, which NASA later identified as a thermal blanket lost during repairs. Yet, blurry images and patchy records fueled speculation, with some pointing to anomalies like its irregular orbit and apparent longevity as proof it wasn't human-made. So what's really out there? Scientists have debunked the myth repeatedly. The signals were likely cosmic noise or early satellite tests, while modern tracking confirms no unknown objects in stable ancient orbits. But the mystery persists for a reason. The Black Knight taps into a deeper fascination, the idea that we're not alone and evidence might be right overhead. Some theorists propose it's a fragment of an advanced precursor civilization, or even a still functional sentinel left by extraterrestrials. Others argue it's a psychological Rorschach test. In the void of space, our minds fill gaps with patterns, turning space junk into something grander. The truth, space is cluttered with defunct satellites, discarded rocket parts, and debris over 500,000 pieces, some tumbling unpredictably for years. Yet the Black Knight endures because it symbolizes a haunting question. If we found proof of alien technology, would we even recognize it? Until then, this cosmic ghost story reminds us that the line between myth and discovery is thinner than we think. We've spent decades scanning the skies, listening for whispers from civilizations beyond our own. With trillions of stars in our galaxy alone, the odds seemed overwhelmingly in our favor. So why, after all this time, has SETI, the search for extraterrestrial intelligence, heard nothing but silence? This cosmic quiet isn't just puzzling, it's deeply unsettling. Statistically, the universe should be buzzing with life. The Drake equation, a famous formula estimating the number of communicative civilizations, suggests we shouldn't be alone. And yet, the radio telescopes remain stubbornly quiet. This isn't just a scientific hurdle, it's a paradox that forces us to confront some of the most chilling possibilities imaginable. One explanation is the dark forest theory, inspired by the idea that the cosmos might be less like a bustling metropolis and more like a predator-filled jungle. Imagine every civilization is a hunter hiding in the trees, terrified of being discovered. Broadcasting your location could invite disaster, perhaps from ruthless civilizations that eliminate competitors before they become threats. In this scenario, silence isn't just a choice, it's survival. The universe appears empty not because it is, but because everyone is too afraid to speak up. Then there's the Great Filter hypothesis, a cosmic bottleneck that prevents life from advancing to the stars. Maybe the leap from simple cells to complex intelligence is so unlikely we're the fluke. Or worse, the filter lies ahead of us. Perhaps every advanced civilization hits a self-destructive wall, whether through war, environmental collapse, or unchecked technology. If that's true, our silence might be a countdown clock, but not all explanations are doom-laden. Some suggest we're simply looking in the wrong way. What if advanced civilizations communicate via neutrino beams or quantum entanglement, methods we haven't even begun to decode? Or consider the zoo hypothesis, where aliens observe us from afar, respecting a cosmic prime directive. There's also the possibility we're early to the party, that intelligent life is rare now but will flourish in the distant future when conditions are more favorable. The Great Silence isn't just a scientific mystery, it's a mirror. Every theory reflects our deepest hopes and fears about intelligence, survival, and our place in the universe. Whether the answer is caution, catastrophe, or simple cosmic timing, one thing's certain: the silence speaks volumes, and until we hear otherwise, it remains one of the most profound puzzles ever to echo across the stars. The cosmic microwave background, the faint afterglow of the Big Bang, should be a uniform sea of radiation, a perfect snapshot of the infant universe. But in 2003, data from NASA's Wilkinson microwave anisotropy probe sent shockwaves through cosmology. The CMB wasn't just random noise, it showed an eerie, unexpected pattern. A mysterious axis nicknamed the Axis of Evil, where temperature fluctuations appeared aligned in a way that defied the cosmological principle, the bedrock idea that the universe is the same in all directions. This wasn't just a minor quirk. The alignment pointed toward a possible, preferred direction in the cosmos, as if the universe had a hidden North Star billions of light years across. The implications were staggering. If true, it meant the universe might not be as isotropic, as evenly distributed as we'd assumed. Some regions could fundamentally differ from others, undermining a century of astrophysical models. Skeptics argued it was a statistical fluke, an artifact of measurement bias or foreground interference from our own galaxy. But as more data poured in from missions like Planck, the anomaly stubbornly persisted. One leading theory suggests the alignment traces back to the universe's earliest moments, when quantum fluctuations during inflation might have left an imprint on spacetime itself. Others propose more radical explanations, like the gravitational pull of a neighboring universe in a multiverse scenario, tugging at the fabric of ours. Then there's the unsettling possibility that we're seeing the fingerprints of something even larger, a structure or force beyond our current comprehension. What makes the Axis of Evil so provocative isn't just the data, it's the philosophical rift it exposes. For decades, science has operated under the assumption that we occupy no special place in the cosmos. But if the universe has a preferred axis, does that mean some locations, some directions are fundamentally different? The debate remains open, with some researchers calling for entirely new physics to explain it. Until then, this cosmic riddle lingers, a whisper from the depths of time, challenging us to rethink everything we thought we knew about the universe's symmetry. In October 2017, astronomers spotted something unprecedented racing through our solar system, a visitor from another star. Named Oumuamua, Hawaiian for scout or messenger, this object wasn't just the first known interstellar traveler. It was a shape-shifting enigma that defied every expectation. At first glance, it seemed like a typical comet until it started accelerating. Unlike comets, which speed up when sunlight vaporizes their icy surfaces, Oumuamua gained momentum without the telltale puff of gas or dust. No tail, no coma, just silent, inexplicable propulsion. And then there was its shape. Estimates suggested it was 10 times longer than it was wide, tumbling end over end like a cosmic cigar, a form never before seen in nature. Theories erupted. Harvard astrophysicist Avi Loeb made headlines by proposing the unthinkable. Could Oumuamua be artificial? a light sail perhaps propelled by starlight, a discarded relic, or even an active probe from a distant civilization. The idea wasn't entirely fringe. Human projects like Breakthrough Starshot aim to send tiny light sails to nearby stars, using lasers to push them to relativistic speeds. If we've imagined it, why couldn't someone else have built it? Skeptics countered fiercely. Maybe Oumuamua was a rare type of hydrogen iceberg, its acceleration caused by evaporating hydrogen too faint to detect. Or a fractal-like dust aggregate, porous enough to be pushed by sunlight without leaving debris. Yet every explanation had holes. Hydrogen ice should have vaporized long before reaching our solar system. Dust structures that fragile wouldn't survive the journey. Even the comet theory faltered. Follow-up observations found no water or carbon dioxide, the usual suspects behind outgassing. The truth is, Oumuamua's brief visit left more questions than answers. By the time telescopes turned toward it, the object was already fading into the darkness, carrying its secrets back to interstellar space. What makes this cosmic scout so haunting isn't just the mystery of what it was. It's the realization of how much we might be missing. Most interstellar objects likely pass unnoticed, too small or dark to detect. Oumuamua was a fluke, a glimpse of something extraordinary. Was it a fragment of a shattered planet, a bizarre new class of celestial body, or, as Loeb dared to suggest, evidence that we're not alone? Until another visitor arrives, the debate rages on, a reminder that sometimes the most profound discoveries are the ones that slip away before we can understand them. Deep in the constellation Boötes lies a vast, eerie nothingness, a cosmic desert so enormous it could swallow thousands of galaxies whole. Stretching an astonishing 330 million light-years across, the Boötes void isn't just empty. It defies our most basic understanding of how the universe organizes itself. In a cosmos teeming with galaxies clustered like cities along invisible highways, this region is a ghost town less than 10% as dense as it should be. To put that in perspective, if the universe were a sponge, the Boötes void would be the gaping hole where the structure simply vanishes. When astronomer Robert Kirshner first stumbled upon this anomaly in 1981, the data seemed impossible. Standard models predicted that even the emptiest patches of space should contain at least 2,000 galaxies. Yet the void held only 60, a cosmic oversight so glaring, it forced scientists to question whether their theories had missed something fundamental. How could gravity, which pulls matter into filaments and clusters over billions of years, leave behind a void this vast and stark? Some theorize it's the aftermath of an ancient collision between bubble-like universes in a multiverse, leaving our reality with a scar. Others suggest a nightmarish scenario. What if the void isn't empty at all, but filled with dark matter so exotic it repels ordinary matter like oil pushing away water? The mystery deepens when you consider the void's edges. Most cosmic structures have gradual borders, but the Boötes void drops off sharply, as if someone carved it out with a knife. Stranger still, the few galaxies inside huddle together in a bizarre string of pearls formation, orbiting nothing. Their motion implies the presence of mass we can't see, hinting at hidden forces at work. Could this be evidence of a gravitational anomaly powerful enough to clear galaxies out like a cosmic vacuum? Or is the void teaching us that the universe's structure is far messier, far more unpredictable than our tidy models suggest? What makes the Boötes void so unsettling isn't just its emptiness, it's the unshakable sense that we're peering into a cosmic blind spot. If our theories can't explain such a glaring absence, what else might we be missing? As telescopes probe deeper, this ghostly gap reminds us the universe isn't just stranger than we imagine, it's stranger than we can imagine. Imagine launching 2 spacecraft into the void, meticulously calculating their trajectories using the same physics that guided every mission before them, only to watch, baffled, as they mysteriously slow down. That's exactly what happened with NASA Pioneer 10 and 11, twin probes sent to explore the outer solar system in the 1970s. For decades, these robotic pioneers became the center of one of spaceflight's most persistent puzzles, an unexplained deceleration so slight yet so consistent it hinted at gaps in our understanding of gravity itself. The anomaly was subtle but undeniable. As the probes sped toward the edges of the solar system, tracking data revealed they were losing speed ever so slightly, about 300,000 times weaker than Earth's gravity, but enough to throw off their predicted positions by hundreds of thousands of miles. At first, scientists suspected mundane causes, a fuel leak perhaps, or thermal radiation from the probe's radioactive power sources nudging them off course. But when engineers accounted for every conceivable variable, the slowdown remained. Some theorists proposed radical explanations, new forces, deviations from Einstein's relativity, even the gravitational pull of unseen dark matter clumped near the solar system. Then, in 2012, the mystery cracked. Meticulous computer modeling revealed an overlooked detail: heat. Pioneer's plutonium-powered generators radiated warmth, and as that energy bounced off the spacecraft's dish-shaped antennas, it created a tiny but constant push, like a car's brake pedal being gently tapped by light itself. The effect, called thermal recoil force, had been too faint to notice in previous missions. Once accounted for, the anomaly vanished, case closed, yet the Pioneer anomaly's legacy endures. It's a humbling lesson in how even the tiniest forces can upend our assumptions when precision matters. Future missions, like those to interstellar space, now factor in thermal effects with painstaking detail. But deeper questions linger. How many other solved anomalies might hide truths we've yet to recognize? And what happens when the next deviation defies all our models? The pioneers taught us that in the vast, silent reaches of space, even the smallest whispers can force science to listen and rethink. Galaxies aren't the serene islands of stars we once imagined. They're cosmic predators locked in a silent, slow-motion struggle for survival. Take Andromeda, our closest galactic neighbor. It may look like a tranquil spiral from a distance, but zoom in, and you'll find evidence of a violent past: streams of stars torn from smaller galaxies, ghostly halos of debris, and the telltale scars of a celestial feast. This isn't science fiction, it's galactic cannibalism, a process so chaotic it's rewriting our understanding of how galaxies grow. For decades, astronomers assumed galaxies evolved peacefully, gently accumulating gas and dust to form new stars. But the discovery of tidal streams, long ribbons of stars ripped from dwarf galaxies and stretched across space, painted a far more dramatic picture. Andromeda alone has devoured dozens of smaller galaxies, leaving behind a graveyard of stellar remnants. One victim, a dwarf galaxy called M32, was reduced to a dense core, its outer layers stripped away like flesh from bone. Another, the Triangulum galaxy, now orbits Andromeda like a wounded animal, its fate all but sealed. What makes this process so surprising isn't just the violence, it's the scale. Early models predicted galaxies would grow by sucking in gas, not shredding entire star systems. Yet the evidence is everywhere. Our own Milky Way is no exception. It's currently digesting the Sagittarius dwarf spheroidal, a galaxy it's been tearing apart for billions of years. The remnants of this feast swirl around us, a silent testament to the chaos hidden in plain sight. The implications are profound. Galactic cannibalism challenges the idea of predictable cosmic evolution, revealing a universe where brute force often trumps orderly growth. It also raises eerie questions. If large galaxies thrive by consuming smaller ones, what does that mean for the future of our own Milky Way? In 4 billion years, Andromeda will collide with us, triggering a cannibalistic merger that will reshape both galaxies forever. But here's the twist. This destruction fuels creation. The chaos of galactic collisions triggers bursts of star formation, seeding new generations of stars from the wreckage. In a way, cannibalism isn't just about death. It's a cosmic recycling program where the bones of old galaxies become the building blocks of new ones. This violent dance forces us to rethink our place in the universe. We're not just inhabitants of a stable galaxy, we're living in the aftermath of ancient carnage on a collision course with another predator. The cosmos isn't a static museum, it's a living, breathing arena where even the mightiest structures are shaped by forces as primal as hunger. We think we know what the universe is made of: atoms, particles, the stuff you and I and every star are built from. Scientists call this ordinary matter baryonic matter, and according to our best models, it should make up about 5% of the cosmos. But here's the catch: when astronomers tally up all the visible galaxies, stars, and gas clouds, nearly half of that expected matter is missing. This is the missing baryon problem, one of cosmology's most embarrassing gaps, like misplacing half the ingredients in a recipe and still expecting the cake to turn out right. For decades, the search for these lost baryons felt like chasing shadows. They don't glow like stars or block light like dark matter, so traditional telescopes couldn't spot them. But theorists had a hunch: if the missing matter existed, it must be hiding in the diffuse threads of the cosmic web, the vast, invisible scaffolding of gas and plasma that stretches between galaxies. Picture the universe as a sponge, with galaxies clinging to the dense strands and the rest of the space filled with wispy, ionized gas too faint to see. Then, in 2017, two teams of astronomers finally caught a break. Using the European Space Agency's XMM Newton telescope and NASA's Chandra X-ray Observatory, they detected the faint glow of superheated oxygen gas in the spaces between galaxy clusters. This wasn't just any gas, it was scorching at millions of degrees, emitting X-rays so subtle they'd gone unnoticed for years. By mapping these whispers of radiation, scientists confirmed the missing baryons were there all along, woven into the cosmic web like threads in a tapestry. But the mystery doesn't end there. How did this gas get so hot? One theory points to shockwaves from the births and deaths of galaxies, pumping energy into the web like cosmic sound waves. Others suggest black holes might be involved, their jets heating the gas to extreme temperatures. And then there's the lingering question: does this discovery account for all the missing matter, or are there still pockets lurking in even harder to detect forms? What makes this anomaly so fascinating isn't just the solution, it's the lesson. Even the most fundamental assumptions about the universe can hide blind spots. For years, we overlooked matter not because it wasn't there, but because we didn't know how to look. Now, as new telescopes like the James Webb Space Telescope peer deeper into the cosmic web, we're reminded that the universe's greatest secrets might not be in the dazzling stars or swirling galaxies, but in the quiet, overlooked spaces between them. Most nebulas are cosmic splatters, amorphous clouds of gas and dust painted across the void by the brushstrokes of stellar winds and explosions. Then there's the Red Rectangle Nebula, a cosmic structure so precise it looks like it was drafted with a ruler. Located about 2,300 light-years away in the constellation Monoceros, this glowing geometric anomaly defies every expectation of how dying stars behave. At its heart lies HD 44179, a binary star system where one star has reached the end of its life, puffing off layers of gas in what should be a chaotic, spherical farewell. Yet instead of a messy stellar death, we see a near-perfect rectangle with ladder-like rungs of glowing material stretching outward, as if the universe suddenly decided to follow the rules of architecture. The strangeness doesn't stop at its shape. The nebula's vivid red hue comes from an unexpected chemical cocktail: complex organic molecules called polycyclic aromatic hydrocarbons, or PAH. These are the same compounds found in soot and interstellar dust, but here they're arranged in dense, concentric rings, almost like tree rings recording the star's death throes. Even more bizarre, the red rectangle emits an eerie blue luminescence, a phenomenon called fluorescence, where UV light from the central stars gets absorbed and re-emitted by the surrounding gas. This two-tone spectacle makes it one of the most photogenic yet least understood objects in the sky. So how did nature craft something so unnervingly symmetrical? The leading theory points to the binary stars themselves. As the dying star sheds material, its companion star's gravity shapes the outflow into two cones, which we see edge on, creating the illusion of a rectangle. The rungs might be shockwaves, ripples from periodic bursts of material ejected by the stars, but even this explanation feels incomplete. Why are the rungs so evenly spaced? Why do the PAHs form such orderly rings? Some researchers speculate magnetic fields are at play, sculpting the gas like invisible hands. Others wonder if we're witnessing a rare phase of stellar evolution, one that only occurs under perfect, fleeting conditions. Then there's the tantalizing possibility that the red rectangle isn't just a cosmic oddity, it's a preview. PAHs are considered building blocks for more complex molecules, the kind that could seed life elsewhere. Could nebulae like this be factories for organic chemistry, quietly assembling the ingredients of biology in deep space? The answer might lie in the nebula's eventual fate. In a few thousand years, the central stars will heat up, illuminating the expelled gas and transforming the red rectangle into a full-fledged planetary nebula, a stage that could reveal even more secrets. For now, this crimson enigma remains a masterpiece of celestial geometry, a reminder that even in the chaos of the cosmos, there's room for precision and mystery. The observable universe follows certain unspoken rules. Structures shouldn't grow beyond a reasonable size, given the time and physics we understand. Yet suspended in the darkness, stretching an almost unimaginable 10 billion light-years across, lies an object so vast it makes our entire local supercluster look like a speck, the Hercules Corona Borealis Great Wall. Discovered in 2013 by mapping gamma-ray bursts the death cries of massive stars. This titanic filament of galaxies isn't just large, it's too large. A cosmic leviathan that, by all accounts, shouldn't exist. Here's the problem. According to the cosmological principle, the universe should look roughly the same no matter where you're standing. Matter ought to distribute evenly on the grandest scales, with no single structure dominating. Yet the Great Wall defies this, spanning nearly a tenth of the observable universe. If it were a country, the cosmic speed limit, light itself, would take 10 billion years to cross its borders. To put that in perspective, Earth hadn't even formed when light from one end began its journey toward the other. The discovery sent shockwaves through cosmology. How could gravity assemble something so enormous in just 13.8 billion years? One theory suggests the Great Wall isn't a single structure but a chance alignment of smaller filaments, a trick of perspective. But gamma-ray bursts don't lie. They trace the densest patches of matter, and their pattern reveals a connected web. Others propose dark energy, the mysterious force accelerating the universe's expansion, might have sculpted it by slowing growth in surrounding regions, leaving this one grotesquely overdeveloped. The most radical idea, that the Great Wall is evidence of a pre-Big Bang structure, a relic from a previous cosmic cycle. If true, it would upend our understanding of the universe's birth. Skeptics counter that our models simply need tweaking, that we're seeing the upper limits of large-scale structure formation for the first time. But even that admission carries weight. Either way, the Hercules Corona Borealis Great Wall stands as a humbling reminder. The universe doesn't care about our expectations. It builds what it pleases on scales we're only beginning to comprehend. What makes this anomaly so profound isn't just its size. It's the questions it forces us to confront. Are we missing a fundamental piece of cosmic evolution? Could there be even larger structures lurking beyond our observational limits? Until we peer deeper into the void, this gargantuan wall remains both a landmark and a taunt, a cosmic challenge written across the sky. The moon seems like a quiet, unchanging neighbor, a barren rock frozen in time. But pick up one of its ancient stones and you'll find a ghostly whisper from its past: magnetism. Here's the puzzle. Today, the Moon has no global magnetic field, yet samples brought back by Apollo astronauts contain rocks magnetized as if they'd cooled in the presence of a powerful one. Some of these lunar materials date back over 3 billion years, bearing magnetic signatures stronger than Earth's current field. How could a world now so magnetically dead have once been so alive? The leading theory points to a long-lost lunar dynamo, a churning core of molten metal that once generated a magnetic field much like Earth's does today. But here's where things get weird. Earth's dynamo is powered by its massive, still molten core and rapid spin. The Moon, by contrast, is tiny, just 1% of Earth's mass, with a core that should have cooled and solidified billions of years ago. Even stranger, some magnetized rocks suggest the Moon's field persisted for over 1 billion years, far longer than conventional models predict. One radical idea involves a gravitational tug-of-war with Earth. Early in its history, the Moon orbited much closer, and our planet's gravity may have stirred its core like a spoon in molten iron, a process called mechanical dynamo action. Others propose that tidal heating from repeated asteroid impacts kept the core churning, or that the Moon's core crystallized in a way that released latent heat, fueling the dynamo far longer than expected. There's even a wild card theory. Short-lived radioactive elements in the lunar mantle could have acted like cosmic batteries, pumping energy into the core. Yet none of these explanations fully account for the strength and duration of the Moon's ancient magnetism. Some magnetized rocks imply fields up to 100 microteslas, twice as strong as Earth's field today. How could such a small world generate such power? The answer might lie in the dynamo's structure. Recent computer simulations suggest the Moon's core could have been stratified, with layers of molten metal moving at different speeds, amplifying the magnetic field like a cosmic amplifier. The implications reach far beyond lunar geology. If the Moon's dynamo lasted longer than thought, it rewrites the rules for how small rocky bodies evolve. Exomoons around distant planets might harbor similar surprises, hidden oceans or magnetic shields that make them unexpected havens for life. And then there's the haunting possibility that other seemingly dead worlds in our solar system, like Mercury or even Mars, might have had far more dynamic pasts than we've assumed. For now, the Moon keeps its secrets locked in those magnetized rocks, each one a tiny time capsule from an era when our celestial companion wasn't just a silent observer, but a world with a beating metallic heart. Every new lunar mission peels back another layer of the mystery, reminding us that even the familiar can hold extraordinary surprises. For centuries, astronomers believed the universe's expansion was slowing down, a gradual coasting after the explosive sprint of the Big Bang. Gravity, after all, was the ultimate cosmic brake, pulling everything back together. Then, in 1998, two teams studying distant supernova dropped a bombshell. The universe wasn't just expanding, it was accelerating. It was like tossing a ball into the air, only to watch it rocket away faster and faster, defying gravity's grasp. This discovery flipped cosmology on its head, earning the researchers a Nobel Prize and forcing scientists to confront an unsettling truth: something invisible, something powerful, was pushing the cosmos apart. They called it dark energy, a placeholder name for a force we still don't understand. The evidence came from Type 1, a supernova, stellar explosions so uniform they're nicknamed standard candles. By measuring their brightness across vast distances, researchers could gauge how fast the universe was stretching over time. The faintness of these ancient supernovae revealed a startling pattern. Galaxies farther away were receding faster than expected, as if space itself had a hidden throttle. Follow-up studies of the cosmic microwave background and large-scale galaxy distributions confirmed it. Dark energy wasn't just real. It dominated the universe, making up nearly 70% of its total energy. So what is it? The leading candidate is the cosmological constant, a term Einstein once inserted and later discarded in his equations to balance gravity. It suggests empty space isn't truly empty. It seethes with latent energy that drives expansion, but there's a problem. Quantum theory predicts this energy should be unfathomably stronger, up to 120 orders of magnitude, than what we observe. This mismatch, called the cosmological constant problem, is arguably the worst prediction in physics. Alternative theories abound. Maybe dark energy isn't constant but evolves over time, a concept called quintessence. Or perhaps Einstein's gravity equations break down on cosmic scales, requiring entirely new physics. Some even propose extra dimensions leaking gravity into our universe, subtly altering expansion. Yet every explanation has flaws. If dark energy changes, why haven't we detected its fluctuations? If gravity's laws are wrong, why do they work perfectly everywhere else? The most haunting possibility: dark energy might not be a force at all, but a sign we've misread the universe entirely. Could acceleration be an illusion caused by our galaxy sitting in a vast void where fewer nearby galaxies tug on us? Or is it a statistical fluke, a trick of how we measure distances? Both ideas have been largely ruled out, but they underscore how much we're groping in the dark. What makes dark energy so unnerving isn't just its mystery, it's the stakes. If it strengthens over time, it could tear apart galaxies, stars, even atoms in a big rip. If it weakens, gravity might regain control, collapsing the universe in a big crunch. Or it might just fade quietly, leaving the cosmos to expand forever into cold, empty darkness. For now, dark energy remains the ultimate cosmic wild card, a reminder that the universe's greatest forces might be the ones we can't see. Every new telescope, every deeper sky survey brings us closer to answers, or perhaps to even bigger questions. One thing's certain: the cosmos isn't just expanding, so is our understanding of how little we truly know. On clear nights, just after sunset or before dawn, you might spot a faint, eerie glow stretching upward from the horizon, a triangular shimmer often mistaken for twilight. This is the zodiacal light, sunlight scattered by dust particles drifting through the inner solar system. For centuries, it was considered a simple byproduct of planet formation, leftover debris from the birth of planets 4.5 billion years ago. But recent observations have turned this assumption upside down. The dust creating this cosmic glow isn't ancient, it's being replenished and far faster than our models can explain. The mystery begins with the dust itself. If the zodiacal cloud were truly primordial, it should have dissipated long ago. Solar radiation and gravitational tugs from planets act like cosmic brooms, sweeping particles away or plunging them into the sun within mere thousands of years. Yet the glow persists bright and steady, implying a constant influx of new material. Where's it all coming from? The prime suspects are asteroid collisions. When rocky bodies smash together in the main belt between Mars and Jupiter, they generate fresh debris, some of which spirals inward over time, feeding the zodiacal dust cloud. But here's the catch: even the most generous estimates of asteroid smash-ups can't account for the sheer volume of dust we see. Enter the paradox. Models predict the zodiacal light should be at least 10 times dimmer based on known collision rates. Some hidden process must be pumping dust into the system at an unexpected scale. One tantalizing clue comes from Jupiter's Trojan asteroid swarms of rocks trapped in the gas giant's orbit. Recent studies suggest these Trojans might be far dustier than we thought, shedding material through micro-collisions or thermal fracturing as they cycle between sunlight and shadow. Another theory points to comets. As these icy wanderers disintegrate near the sun, they could seed the inner solar system with fine particles, though again, the numbers don't quite add up. Then there's the wild card: interstellar interlopers. Objects like Oumuamua and Borisov have proven that visitors from other star systems occasionally drift through our neighborhood. Could similar, unseen bodies be crumbling apart, seeding our solar system with foreign dust? It's a stretch, but not impossible. The alternative, that we've fundamentally misunderstood how asteroid collisions generate and distribute debris, would be equally groundbreaking. What makes this cosmic whodunit so compelling isn't just the missing dust. It's what the solution could reveal about the solar system's hidden dynamics. Every speck in that glow carries clues about the violence of asteroid belts, the life cycles of comets, even the possibility of unseen objects lurking in the darkness. For now, the zodiacal light remains both a beacon and a riddle, shimmering proof that even in our own celestial backyard, the simplest questions can defy explanation. Most galaxies follow familiar blueprint spirals with sweeping arms, ellipticals like cosmic blobs or chaotic irregulars. Then there's Hoag's object, a galaxy so bizarre, it looks like someone dropped a celestial smoke ring into the void. Discovered in 1950 by astronomer Art Hoag, this perfect ring of young blue stars glows against the darkness, encircling a golden core of ancient stars. But here's what makes it truly strange. Between the vibrant outer ring and the core lies an empty gap, a stark, starless chasm stretching tens of thousands of light years. No spiral arms, no connecting threads, just a cosmic bullseye floating in isolation. Ring galaxies themselves aren't unheard of. Usually, they form through colossal collisions, like the Cartwheel Galaxy, where a smaller galaxy punched through a larger one, sending shockwaves through its dust and gas, triggering star formation in a rippling ring. But Hoag's object defies this explanation. There's no sign of a recent impact, no debris trail, no surviving intruder galaxy. It's pristine, symmetrical, and eerily alone. So how did this cosmic oddity form? One theory suggests a slow-motion merger billions of years ago, where a smaller galaxy was absorbed so cleanly only the ripples remain. Another proposes a rare instability in the galaxy's original disk, causing stars to migrate inward and outward, leaving the gap. The wildest idea, that Hoag's object is a polar ring galaxy seen perfectly edge-on, a type where a second ring orbits perpendicular to the main disk, though even this doesn't fully explain its symmetry. What makes Hoag's object even more fascinating is its company. Peering deeper into its background reveals another, fainter ring galaxy, an unlikely alignment that hints these structures might be more common than we thought. Yet none match Hoag's perfection. It's a galactic unicorn challenging our assumptions about how galaxies live, evolve, and sometimes defy every known script. Whether it's a fossil of a forgotten collision or a fluke of cosmic physics, one thing's certain: this celestial enigma reminds us that even in a universe of patterns, there's always room for a beautiful outlier. High-energy cosmic rays shouldn't be able to reach us, at least not according to our best understanding of the universe. These particles, traveling at nearly the speed of light, pack more energy than anything produced in our most powerful particle colliders. Yet when they streak through Earth's atmosphere, they defy a fundamental cosmic rule. In 1966, physicists Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin predicted a hard limit for these rays, now known as the GZK cutoff. Their theory was simple: the universe itself should act like a giant roadblock. The cosmic microwave background, the afterglow of the Big Bang, fills every inch of space, and when ultra-high-energy cosmic rays collide with these ancient photons, they should lose energy rapidly, like a marathon runner slamming into a wall. Over long distances, this interaction should drain them completely, making it impossible for the highest energy rays to reach us from distant galaxies. But the universe loves a good paradox. In the late 1990s, observatories like the Pierre Auger Array began detecting cosmic rays with energies far beyond the GZK cutoff, particles so energetic they shouldn't exist in our neighborhood. It's like finding a snowball that somehow survived a trip through a blast furnace. So how are they getting here? One radical explanation suggests the laws of physics might bend under extreme conditions. Lorentz invariance, a cornerstone of Einstein's relativity, states that the laws of physics remain the same no matter how fast you're moving. But if this symmetry breaks down at ultra-high energies, particles could cheat the system, slipping past the CMB's barriers like ghosts through a wall. Not everyone's convinced. Alternative theories propose that these rays come from much closer than we think, perhaps from hyperactive supermassive black holes in nearby galaxies, or even from exotic dark matter annihilations in our own cosmic backyard. Others speculate the rays might be composite particles, clumps of matter that disperse their energy in ways we don't yet understand. Then there's the unsettling possibility that we're misinterpreting the data entirely. What if the highest energy events aren't cosmic rays at all, but something stranger like defects in spacetime itself? The Decode Paradox isn't just a puzzle, it's a potential window into new physics. If Lorentz violation is real, it could rewrite our understanding of reality's fundamental rules. If not, then something equally profound is feeding us these cosmic misfits. Every detected ray is a challenge, a dare from the universe to think bigger, dig deeper, and question what we think we know. The answers, when they come, might not just solve a cosmic riddle, they could redefine the boundaries of the possible. Saturn's North Pole hides one of the most perplexing weather patterns in the solar system, a colossal hexagon wider than Earth itself, etched into the planet's atmosphere like a cosmic fingerprint. Discovered by Voyager in the 1980s and later studied by Cassini, this six-sided jet stream rages at speeds over 300 miles per hour, its geometric precision defying every expectation of how planetary storms behave. Unlike the chaotic cyclones of Jupiter or the fleeting tempests of Earth, Saturn's hexagon is unnervingly stable, maintaining its shape for at least 40 years, possibly centuries, without wavering. The strangest part, nature abhors straight edges. From soap bubbles to galaxies, fluid dynamics and gravity sculpt curves, not angles. So how does a planet known for its elegant rings produce a storm so rigidly geometric? Laboratory experiments on Earth offer tantalizing clues. When scientists spin a circular tank of fluid mimicking Saturn's atmosphere, at just the right speed, something remarkable happens. Waves of varying speeds interact, creating stable, polygonal shapes at the center. The hexagon emerges when the fluid's rotation matches certain ratios, suggesting Saturn's polar winds might be locked in a delicate dance of opposing currents. But here's the catch. These lab models require perfectly controlled conditions, while Saturn's atmosphere is a turbulent soup of hydrogen, helium, and violent storms. How such precision survives in that chaos remains a puzzle. Some theorists propose the hexagon's stability comes from depth, a towering structure extending hundreds of miles downward, anchored by deeper, slower-moving layers of gas. Others speculate it's a standing wave, a ripple frozen in time by the planet's rapid rotation. What makes Saturn's hexagon truly unique isn't just its shape, it's the isolation. No other planet, moon, or cosmic phenomenon exhibits such a persistent geometric storm. Even Jupiter's polar cyclones, though organized into geometric clusters, lack the razor-sharp edges of Saturn's masterpiece. This anomaly forces us to reconsider the fundamentals of fluid dynamics on planetary scales. Could similar structures lurk in the atmospheres of exoplanets, or is this hexagon a fluke of Saturn's specific conditions, its size, spin, or internal heat? The hexagon's endurance raises deeper questions. Most planetary storms feed off temperature gradients or moisture, yet Saturn's hexagon persists in the frigid, dry polar darkness, powered by forces we barely understand. It's a reminder that even in our own celestial neighborhood, nature holds back its strangest tricks, revealing them only to those patient enough to look and humble enough to admit how much they still don't know. The cosmic microwave background is often called the universe's baby picture, a near-uniform snapshot of the cosmos just 380,000 years after the Big Bang. But like any childhood photo, it has its blemishes. One stands out, a chilling void lurking in the constellation Eridanus, a patch of sky roughly 5 times colder than its surroundings. Dubbed the CMB cold spot, this cosmic bruise spans nearly 200 million light-years, an emptiness so profound it defies easy explanation. First spotted in 2004 by NASA's Wilkinson microwave anisotropy probe, the cold spot wasn't just unusually frigid. Its temperature distribution followed no known pattern. Normally, such fluctuations are tiny, random ripples from the universe's infancy, but this was different, the odds of it occurring by chance less than 1 in 50. Initially, scientists suspected a supervoid, an enormous region of space with far fewer galaxies than average. The logic was simple. As light travels through such voids, it loses energy climbing out of their gravitational wells, shifting toward colder temperatures, a phenomenon called the integrated Sachs-Wolf effect. But when astronomers mapped the cold spot's neighborhood, the mystery deepened. While it sits near a sparse region, the void isn't nearly large or empty enough to account for the temperature drop. It's like finding an ice cube in the desert and realizing the shadow from a lone cactus couldn't possibly have created it. This mismatch sparked wilder theories, including one that sounds ripped from science fiction. The cold spot might be a cosmic bruise left by a collision with another universe. In this scenario, our universe isn't alone but part of a multiverse, a frothing ocean of bubble realities. If another bubble nudged ours during inflation, the rapid expansion right after the Big Bang, it could have left behind a subtle dent in space-time, a cold imprint where energy was drained away. The idea isn't entirely fringe. Some models of eternal inflation predict such collisions, but proving it, that's another story. Skeptics argue the cold spot could still be a statistical fluke, an artifact of how we analyze the CMB's noise. Others propose more mundane physics. Perhaps an immense cluster of dark matter warps light in ways we don't yet understand. What makes the cold spot so unnerving isn't just its existence, it's the stakes. If it's truly a window into the multiverse, it could be the first tangible evidence that our cosmos is just one of many. If it's a supervoid, it challenges our understanding of how large-scale structures form. And if it's just noise, then our statistical models might need an overhaul. Every new observation peels back another layer, but the core question remains: is this a clue to realities beyond our own, or just a trick of the cosmic light? Until we know for sure, the cold spot lingers a ghostly fingerprint on the universe's oldest canvas. Black holes come in extremes, the gargantuan supermassive monsters anchoring galaxies, and the stellar mass remnants of collapsed stars. But what about the cosmic misfits in between? Meet the unicorn, a black hole so small, so elusive, it shouldn't exist. At just 3 times the mass of our Sun, this peculiar object dances along the edge of a theoretical no-man's land known as the mass gap, a mysterious void where black holes weren't supposed to form. Its discovery in 2021 sent shockwaves through astrophysics, forcing us to rewrite the rules of stellar death. The mass gap has long puzzled scientists. When massive stars die, theory predicts 2 possible fates. Lighter stars collapse into dense neutron stars, no heavier than 2.5 solar masses, while heavier ones become black holes, typically weighing at least 5 times the Sun. The gap between these extremes was thought to be barren, a cosmic dead zone where gravity simply couldn't compress matter into a black hole. Then along came the unicorn, lurking just 1,500 light-years away in the constellation Monoceros. Astronomers didn't spot it directly. Instead, they noticed a red giant star nearby wobbling strangely, as if tugged by an invisible companion. Calculations revealed an object too dark to be a star, too massive to be a neutron star, a quiet rebel defying classification. What makes the unicorn so revolutionary isn't just its size, it's the way it formed. Traditional models suggest black holes in this mass range could only arise from rare mergers of neutron stars, yet there's no evidence of such violence here. Instead, this black hole might be a primordial relic, born in the chaos of the early universe under conditions we've yet to imagine. Or perhaps our understanding of stellar collapse is fundamentally incomplete. Some theorists now propose that certain stars might shed just enough material in their death throes to skirt the neutron star limit, quietly crossing into black hole territory without fanfare. The implications ripple far beyond one oddball object. If the unicorn isn't alone, if the mass gap is peppered with similar black holes, it could reshape how we interpret gravitational wave signals from colliding stars. It might even hint at hidden populations of dark, quiet black holes drifting unseen through our galaxy, a ghostly census we're only beginning to uncover. Every new observation chips away at the gap's mystery, blurring the line between neutron stars and black holes until one day, perhaps, the gap itself will vanish, erased by the very anomalies it once excluded. For now, the unicorn remains a cosmic whisper, a challenge scribbled in gravity's handwriting. It reminds us that the universe doesn't follow tidy rules. It invents them as it goes, leaving us to piece together the story one paradoxical discovery at a time. Galaxies spin like celestial whirlpools, their stars swirling around the center in a delicate gravitational ballet. But when astronomers first measured these rotations, they stumbled upon something bizarre. The outer stars were moving far too fast. According to Newton's laws, these distant stars should be sluggish, their speed dropping off as they orbit farther from the galaxy's core. Instead, they whip around as if gripped by invisible hands. This was our first clue that galaxies are wrapped in halos of dark matter, an unseen substance whose gravity keeps stars from flying into the void. Yet there's a twist in this cosmic detective story. When scientists simulate how dark matter should behave given what we know about gravity and the universe's structure, something doesn't add up. The simulations predict dense, clumpy halos with dark matter piling up in certain regions and thinning out in others. But reality paints a different picture. Take dwarf galaxies, for example. These small, faint satellites orbiting larger galaxies should, according to the models, be packed with dark matter at their cores. Instead, many show surprisingly even distributions, as if some force has smoothed out the invisible scaffolding. This mismatch, known as the core cusp problem, has become one of the most stubborn puzzles in modern cosmology. Dive deeper and the anomalies multiply. In some galaxies, like the ultra-diffuse Dragonfly 44, dark matter seems to dominate almost entirely, making up 99% of its mass despite having almost no visible stars. Others, like NGC 1052DF2, appear nearly devoid of dark matter altogether, a cosmic ghost town where the rules seem reversed. These outliers defy the standard playbook where dark and visible matter are thought to evolve together. What's causing this cosmic disconnect? One radical possibility is that we've misunderstood dark matter's nature. Maybe it isn't the cold, slow-moving particles we've long assumed, but something more dynamic, particles that interact with each other through unknown forces, creating a kind of dark physics that redistributes mass in ways we can't yet model. Another theory suggests gravity itself works differently on galactic scales, a hypothesis known as modified Newtonian dynamics, or MUND. While MUND can explain some rotation curves without invoking dark matter, it struggles with larger-scale phenomena like the bending of light around galaxy clusters. The stakes couldn't be higher. Dark matter isn't just some cosmic placeholder, it's the hidden architecture of the universe, the framework upon which galaxies are built. If our maps of its distribution are wrong, it could mean rewriting the story of how everything from the tiniest dwarf galaxy to the largest supercluster came to be. Every new observation, every galactic oddity, adds another piece to the puzzle, pushing us closer to an answer that might just redefine the universe as we know it. Until then, these ghostly discrepancies linger, silent reminders that the cosmos still holds its deepest secrets close. We take for granted that the universe has one speed, one rate at which it's always been expanding. But what if that assumption is wrong? The Hubble tension isn't just a minor disagreement among scientists, it's a full-blown crisis in cosmology. A discrepancy so stubborn it could rewrite the rules we thought governed everything. Here's the problem. When we measure how fast the universe is expanding today using nearby stars and supernova, we get one number. But when we calculate it using the ancient light of the cosmic microwave background, the afterglow of the Big Bang, we get a different, significantly slower rate. These aren't small margins of error. The gap between them is too wide to dismiss, suggesting something fundamental is missing from our cosmic playbook. This rift first emerged in the early 2000s as telescope technology sharpened enough to reveal the inconsistency. Initially, astronomers assumed it was an observational fluke, a miscalibration or hidden bias in the data. But as measurements grew more precise, the tension only worsened. Independent methods like tracking the flicker of distant quasars or mapping the distribution of galaxies kept landing in the same unsettling no man's land between the two values. The implications are staggering. If both measurements are correct, it means the universe didn't expand at a steady pace. Something must have altered the rate over time, a cosmic curveball our models never anticipated. So what's really going on? One camp argues for new physics of forces or particles beyond the standard model that tweak the universe's expansion. Perhaps dark energy, the mysterious force accelerating the cosmos, isn't constant but evolves, growing stronger or weaker over time. Others propose a hidden population of dark radiation, exotic particles like sterile neutrinos that flooded the early universe, subtly warping its expansion history. There's even speculation that gravity itself behaves differently on cosmic scales, bending the rules we've relied on since Einstein. Then there's the unsettling possibility that we've misread the cosmos entirely. Could the Hubble tension be a sign that we occupy a vast, underdense region of space, a cosmic bubble where expansion rates differ from the broader universe? If true, it would mean our entire neighborhood is an outlier, skewing our measurements like a ship's crew mistaking a quiet bay for the open ocean. But the most tantalizing explanation: that we're witnessing the first cracks in our understanding of the Big Bang itself. The cosmic microwave background is our most sacred relic, the foundation upon which modern cosmology is built. If its predictions no longer align with reality, it could mean the universe's infancy was far more complex than we've imagined, perhaps even hinting at a cyclical cosmos or a multiverse collision. The Hubble tension isn't just a technical debate, it's a philosophical earthquake. For decades, cosmology has operated under the assumption that the universe is uniform, its laws constant. But this discrepancy forces us to confront the unnerving idea that our cosmic neighborhood might be stranger, more dynamic than we ever dared to believe. Every new telescope, from the James Webb to upcoming missions like the Vera Rubin Observatory, brings us closer to answers, or deeper into the unknown. One thing's certain, the universe isn't just expanding, so is our appreciation for just how much we have yet to learn, from the eerie whispers of the wow signal to the gravitational defiance of dark flow. These 25 cosmic anomalies aren't just celestial oddities, they're the universe's way of nudging us off our intellectual couches. Each one, from Saturn's geometric storm to the haunting void of Boötes, forces us to question what we think we know, to rewrite textbooks, and to stare into the abyss with fresh eyes. Consider the Hubble tension, a rift in cosmology so profound it might redefine the Big Bang itself, or the unicorn black hole, a cosmic rebel so tiny it shouldn't exist yet thrives in the shadows. These aren't just puzzles, they're invitations to explore, to doubt, to dream bigger. Science doesn't advance by clinging to comfort, it leaps forward when faced with the inexplicable. The pioneers who first grappled with these mysteries didn't have all the answers, but their curiosity lit the path. Now it's your turn. Which of these cosmic riddles grips your imagination? Is it the chilling silence of Fermi's paradox, hinting that we might be tragically alone or terrifyingly not alone at all? Or the red rectangle nebula, a geometric masterpiece carved by dying stars, whispering secrets about the origins of life itself? Every anomaly we've explored tonight is a thread in the grand tapestry of the cosmos, waiting to be pulled, unraveled, and woven into something new. So keep looking up, stay relentlessly curious, because the universe isn't just stranger than we imagine, it's stranger than we can imagine, and it's not done surprising us yet. If you're hungry for more mind-bending journeys through the cosmos, hit subscribe and join me as we keep chasing the next great mystery. After all, the night sky isn't just a ceiling of stars, it's a question mark written in light, and the best discoveries always begin with a single, irresistible thought: what if?